This is the second part of lecture 6 and we'll start with metal ion catalysis. So the metal ion catalysis, the catalyst who follow this mechanism, they have metal ions. They have bound metal ions with them. Okay, and there are two classes of those: one metal enzymes and metal activated enzymes. And the metal enzymes, they contain tightly bound metal ions, and most commonly transition metal ions such as iron 2, iron 3, etc. And in case of metal activated enzymes, they have loosely bind metal ions from solution. Okay, and usually the alkali and alkaline earth metal ions, sodium, potassium, etc. Okay, and metal ions, they participate in the catalytic process in three major ways. Okay, so when the metal ion enzymes, they do the catalysis, they can do this catalysis through three different way. Okay, one is by binding to substrate to orient them properly for reaction, by mediating oxidation reduction reactions through reversible changes in the metal ions oxidation state, by electrostatically stabilizing or shielding negative charging. Okay, so now let's talk in detail. First, metal ion, they can promote catalysis through charge stabilization, and they do this by acting like a acid. Right? In many metal ion catalyzed reactions, the metal ion acts in much the same way as a proton to neutralize negative charge. That is, it acts as a Lewis acid. So what Lewis acid do? They donate a proton, and this proton, they can neutralize the negative charge, thus do the stabilization. Okay, so metal ions works in a similar fashion. Okay, however, metal ions are more often much more effective catalysts than protons, because metal ions can be present in high concentrations at neutral pH and can have charges greater than +1. For example, the proton, it has only one charge, right? But if you think about this metal iron 2, it has two positive charge. Iron 3, it has three positive charge. So that's why they are kind of, you can say, they are more powerful than proton. Okay, so that's why sometimes metal ions are dubbed as super acids. Okay, so let's try to get this example. So this is an example where catalysis by metal ion is occurring by charge stabilization. Okay, so say this is the metal ion, and in this is a decarboxylation reaction of dimethyl oxaloacetate. Okay, that means a carbon dioxide get released from the dimethyl oxaloacetate. So how metal ion helps in this reaction? So if you look at this structure, so here is the carbon dioxide. So if the carbon dioxide need to be removed, this bond, the bond between this carbon and carbon need to be broken down. Okay, so if this bond breaks, then this carbon dioxide can get released. Okay, and metal ion helps to proceed this reaction by stabilizing the negative charge of this oxygen. Okay, so what happens? Okay, there is already a negative charge here, and when this metal ions comes here, it form a transition binding with the oxygen and also with this oxygen. And when this binding, this bond formation occurs, okay, electron is necessary here, right? So for bond formation, they have to share the electron. So from where this electron comes? From this double bond. This double bond, it breaks down, and the released electron, now they help to form this bond. And because of the, and as this bond breaks down, it facilitates the breaking of this bond. So thus carbon dioxide get released, and this transition form is and this transition form occurs, and this metal ion, it helps to stabilize this transition form. Okay, and eventually this metal ion, they get released from this structure, and thus a decarboxylation of oxaloacetate happens. Okay, so in this reaction, the metal ion helps to stabilize the transition state, the structure of the transition state. Thus, helps the reaction to proceed easily. Okay. Now, metal ions can also promote nucleophilic catalysis via water ionization. Metal ions, they bind with the water, and this bound form can more easily supply hydroxyl ions. Okay, so we know that water can supply hydroxyl ions, but when water is bound with this metalloenzymes, they can more easily supply the hydrogen ions. Okay, and then metal ions promote reactions through charge shielding. This is another way by which metal ions do catalysis through charge shielding. Okay, so let's look at this example. This is the structure of ATP, adenosine triphosphate. Okay, and this is a substrate for kinase reactions where in kinase reactions the ATP supply phosphate group, right? So that means it has three, as they have three phosphate, they can supply one phosphate and becomes ADP. So when they need to, they will supply the phosphate, this phosphate is bound with this structure, right? So that means there is three phosphates. So if ATP wants to donate one phosphate, a chemical bond need to be broken down. Okay, so enzymes do that. How enzymes can do that? Okay, the nucleophilic enzymes, okay, who can attract electron, they can attract this phosphate and can take it away from ATP. However, when the enzyme do that, when the enzyme nucleophilically attack here, this oxygen, they have some electron here, right? Because they're negatively charged, so they have electron. So this electron may repel the attacking nucleophiles. Okay, so the nucleophiles, they lack electron. Oh no, the nucleophile, they can, they have extra electron, free electron. With that free electron, they can attack nucleophilically. However, so the attacking nucleophiles, they have free electron, but with that electron they have to attract this phosphate. Okay, but as this oxygen has electron here, this electron can repel that attacking nucleophiles. Okay, so if they repel, so the reaction will become difficult. Okay, so here comes the metal of the enzyme. So like for example, this metal magnesium 2 plus, okay, they can form a transition, they can form transition bonds with this oxygen. Okay, thus shield this structure. So they are shielding the negative charge of this oxygen. So now this oxygen can no more repel the attacking nucleophiles. So the nucleophiles will attack and will take out the phosphate from here. Okay, so by this way, the metal ions, they facilitate the reaction to occur easily or in more or more fast. Okay. Okay, that was about metal ion catalysis. Now we'll talk about the other mechanism. So electrostatic catalysis. Okay, so in this case, the binding of substrate generally excludes water from an enzyme's active site. When the enzyme, in this mechanism, when the substrate bind in the enzyme's active site, water molecule get released. Okay, and electrostatic reactions are much stronger than they are in aqueous solution. Okay, and sorry, and charge distributions about the active sites of enzymes are arranged so as to stabilize the transition state of the catalyzed reactions. That's why it is called electrostatic catalysis, because the charge distribution are in a way that they stabilize the transition state. Okay, and such rate enhancement, which resembles the form of metal ion catalysis, is termed electrostatic catalysis. Okay, And in several enzymes, these charge distributions guide polar substrates toward the binding sites uh, of that the rates of these enzymatic reactions are greater than their apparent diffusion control limits. Okay. Now catalysis, another mechanism. Catalysis through proximity and orientation effect. So the orientation, it will affect the effectivity of the catalysis and also proximity. Okay, so how close and in what direction they are close to. Okay, these things will affect the catalysis. Okay, so in this mechanism, the reactants must come together with the proper spatial relationship for a reaction to occur. I mean, if the reaction just come together, it will not be enough for this reaction. They have to come together with the proper spatial relationship. Okay, and the molecules react most readily only if they have the proper relative orientation. Okay, and these things, it has a name actually. It is called stereoelectronic assistance or control. So what it is, a molecule may be maximally reactive only when it assumes a conformation that aligns its various orbitals in a way that minimize the electronic energy for its transition state. So basically the goal is the transition state need to be stabilized. Okay, and in this mechanism it is done by proper conformation or alignments of the orbitals of the molecule. Okay, and the enzymes bind substrates in a manner that both aligns and immobilizes them so as to optimize their reactivities, and the free energy required to do so is derived from the specific binding free energy of substrate to enzyme. Okay, that means through the binding energy. Okay, I mean the free energy required for this works are derived from binding energy. Okay, say this is an example. Basically this example is it's an example of proximity effect. Okay, so like for example, in the biomolecular reaction of imidazole with phosphonitrophenyl acetate, the progress of the reaction is conveniently monitored by the appearance of the intensely yellow phosphonictrophenolate ion. Okay, so that means, I mean, in general, I'll not go for very details of this reaction. In general, if there are more of this, that is more phosphonictrophenolate, the reaction will occur more fast. Okay, so I mean in the beginning, the imidazole, it reacts with phosphonitrophenyl acetate and phosphonitrophenolate, and an acetyl imidazolium is formed. But as when the reaction will proceed, more phosphonitrophenolate will appear in the reaction center. Okay, and the reaction will happens more fast, because when it is in this form, it is in the proper orientation. Okay, this is the proper conformation for optimum reaction. Okay, and also as there will be, and also if there is more phosphonictrophenolate, it will can, I mean exert an proximity effect, right? More phosphonitrophenolate means there is more chance there then there is more chance that now these two reactants can come close together. Okay, okay, finally the last mechanism, catalysis by preferential transition state binding. So we can easily understand that in this kind of mechanism, the optimum bindings will occur in the transition state. Okay, so the binding of the transition state to an enzyme with greater affinity than the corresponding substrate or products. That means we know that enzyme binds more specifically with the transition form, not with the original form of the substrates. Okay, and and this transition form of the substrate, that means the substrate need to be distorted to get to be best fit with the enzyme. So enzyme itself actually do that. I mean enzyme do this distortion to the substrate, and this process has a name. It is called rack mechanism. Okay, so in this mechanism the enzymes mechanically strain their substrates toward the transition state geometry through binding sites into which undistorted substrates did not properly fit. Okay, that means the enzyme, they distort the substrate towards its transition state geometry, and thus it becomes the best fit with the enzyme active site. So they can bind optimally with the enzyme now. Okay, and the strained reactant more closely resembles the transition state of the reaction than the corresponding unstrained reactant, and the interactions that preferentially bind the transition state increase its concentration and proportionality increase the reaction rate. Okay, and this is an example. So in this example, the rate of reaction is 315 times faster when, I mean, in this reaction this chemical turns into this chemical. Okay, and but this reaction is more fast if this R group is CH3. Okay, this R group, it can be just hydrogen or it can be CH3. If this R group are CH3, the reaction will be more faster, because if there is CH3, greater steric repulsions between the CH3 groups and the reaction groups will occur. I mean, the enzyme will restrain them. Okay, so if there is hydrogen, the that interaction, that I mean the interaction between the enzyme and the substrate, which will distort the substrate, will be less in comparison if this R group is CH3. I mean, if this R group is CH3, this steric effect, okay, this is this I mean this effect of enzymes to distort it will be greater, more. Okay. Okay, so that was all about enzyme catalytic mechanisms. Thank you for your patience.